Today I'll be talking about the carbon. So, first of all, as Professor mentioned, I came from Japan. I graduated from the PhD not so long time ago. I'm fortunately not so old, so I guess okay. So yes, today we'll be talking about the carbon. I will focus later on the carbon nanotubes. What are those? Hopefully it will be understandable. So where should we start this talk? So I was thinking a bit how to show. I guess everyone here knows the periodic table of the elements and how we should define the important ones in this topic. So I thought, for example, okay, let's start maybe from our body, because I think it's the closest thing we can ever achieve. So let's start from the most common in our body, which is hydrogen and oxygen, which is basically 60% of our body, because it's just the water we have in our body. Second one is the carbon that I will be talking later. It's about 18%. It consists in our body cells and not only. And for this reason, it's quite important also. We, of course, have the nitrogen and different species, also there calcium. And all of those that are highlighted white are in our bodies, and they're used for something. Plus, we have a lot of different elements that are in our bodies too, but are kind of like unused, even the uranium and other stuff like this. So don't get scared because of that. So we'll be talking about today about the carbon. This is like short introduction about the periodic table and so on, period and the symbols and the weight. So let's start from the carbon. This is how it more or less looks like in the schematic. And basically it's composed from 6 electrons, 6 protons, and 6 neutrons. And due to that, we can form different kind of bondings. And this is very important because based on this, how it connects to different carbon atoms, but also to different atoms of different elements, different kind of materials can be achieved. And what do you imagine when you hear the carbon? So some of you might imagine some pencils, some carbon rocks, or even the barbecue, or maybe some cartoons, I don't know. Diamonds also. So basically, carbon is all around us if you just think about it a bit. And I will start from the allotropes a bit. So basically the species of the carbon which are the same, but the bondings are a bit different. So we have the two most commonly known, the diamond and the graphite, which have different types of electrical, thermomechanical, and optical properties. As we know, the diamond is the hardest material ever known. And it's basically transparent, and it's also conductive for the thermic, but insulating in the electrical. On the other hand, we have the graphite, which is composed of the same atoms, but it's just in different structure. So it's basically black, and it's soft, and it's also conductive in the electrical part. But we have also different ones. We have the recently developed, found by the Smalley in 1996, the fullerene, which is looking like a ball, basically. We have carbon nanotubes, which were discovered by Sumio Iijima in 1991. But also we have the graphene, which is quite new material, as you can see, only 7 years. And it already was awarded with the Nobel Prize. And today I will focus on the carbon nanotubes. So one more about the allotropes, how we actually make. So as I said, we have the graphene sheet, which is basically connecting atoms in this kind of structure. And if we will cut off this kind of shape and roll it, we have this kind of ball. If we cut like a rectangle or square and roll it in this way, we'll have a carbon nanotube, which kind of resembles a stick. Or if we just stack many layers of them, like the waffle style, we have the graphite, which is used, for example, in our pencils. There are different types of carbon nanotubes. This is actually not so important, I think. So you can omit. I just mentioned that depending on the number of layers in the carbon nanotubes, we can have the single-walled, because of course one double-walled and multi-walled. And multi-walled, it means up to 20, 30 layers even, which changes the diameter and so on. But when we talk about carbon nanotubes, we also have to consider the size of those. So first of all, we can look at the top. We have this kind of measure. So the Earth, the diameter is about 13,000 kilometers. Then if we go down, we have human bodies, 1 or 2 meters. Then we keep going down. We have the pencil line in half of the millimeters. A bit lower in micrometers, we have already our cells of our bodies. Further on, we can find the visible light range from 350 to 750 nanometers. And as we keep going down up to single nanometers, we can already find carbon nanotubes. So as you can see, they're very thin. You cannot see them with your bare eyes when there's individual one. And a bit later, smaller atoms, basically. But on the other hand, because the diameter is quite small, they can be quite long. They can grow to centimeters. And due to that fact, because they can grow 4 centimeters, actually even to 54 centimeters is the longest one, we can observe how they look like in the group. And they have different properties. For example, the electric conductivity, which is 1,000 times higher than the copper, which is very often used as the conductive in the wires and so on. We have thermal conductivity, which is also higher than copper. We have very high mechanical stiffness, strength. With the same diameter of the wire, carbon nanotube is supposed to hold a weight 100 times higher than the steel, than the best steel. And finally, optically, they are darker than black, as you can see. So they have very high absorption. So how to grow such a carbon nanotubes? This image shows the painting, which is already quite old, by Millet, which is in the Boston Museum. And this guy is basically walking around and throwing seeds on the ground in order to grow some wheat or something. And there's very similar cause for the carbon nanotubes. We need some seeds, some style of seeds to grow carbon nanotubes. And those seeds are the so-called catalyst particles. The silicon substrate here is using like the soil that we can grow on with using some seeds. And then when we apply some high temperature and some ingredients, like in case of plants, water and so on, and sun, here just gas with some compounds of carbon, we can grow carbon nanotubes like this. Just fuel it a bit and it will grow. And this is how it looks like in real life. So it's usually called carbon nanotube forest because it also resembles the structure of the forest like this. And this is already like 2-3 millimeters height, even more. And they are very black. By very black, I will show later how much, but it's more than you can, I think, imagine even. And this is under the microscope, how it looked like. The magnification is not so big, maybe 50,000 times, and you still cannot see exactly how the structure looks like. In order to observe how the carbon nanotubes looks inside, you need the magnification of 1 million times, more or less. So we can imagine that you cannot do that with normal microscope either. And this is quite messy, I would say, slide, but so there are different styles of approach of the application of carbon nanotubes. We can use starting from the structure control, which is more random or more oriented. And also we can use single carbon nanotubes to many like forest ones. And because of that, we can apply to different transistor lamps, transparent electrodes, also, for example, already in the composites, in the tennis rackets, for example, in the cars also. In the paint also happens. So basically, due to that, we have in the material applications and some device applications also. More electronic, more thermic. And yes, and now I will focus more about the kind of application of carbon nanotubes that I think are interesting for you, maybe also. So I think every one of you have heard about lotus leaves, which can basically repel the water and they can form those spherical shaped droplets on the surface. But what is actually the difference between the lotus leaf and the normal table or glass? Why here we have the water spread like this, while here we have the droplets. So basically, this is the definition. You don't, of course, have to remember. But it's basically related to the property which is called hydrophobicity. So basically, the material is kind of repelling the other material in the shape that it can form, for example, the droplets. The higher this repellent strength is, the angle of this kind of here will change, and we call it super hydrophobic materials. And while I talk about it, because this is the structure about the lotus leaf, and as you can already see, it's not smooth. It's not smooth. Basically, it forms some kind of surfaces which are not flat, and with those kind of extensions here, extrusions. And as you can see, we can also use it for cleaning like kind of systems. And this is not only lotus leaf, also butterfly wings have this property, and also birds' feathers have this property. Even though it's a different structure a bit, it also works like this. But what about carbon nanotubes? Because I said I will be talking about carbon nanotubes. Well, this is actually working also the same. If we will plan the carbon nanotube structure in a way that we can observe some pillars all around, it will also be hydrophobic material. And this video here will show you how much. This was prepared by other university I'm using. You can find it actually on YouTube. And this is normal vertically aligned carbon nanotube forest you can observe in typical experiment. You just grow, as I said, throw some seeds and grow from that. And it's on the flexible polymer. And this is the droplet of water. And this is what will happen. See? It doesn't spread on the surface. It will bounce like a ball from the surface. And it's still water. And this is the property I was talking about earlier. This is the property called hydrophobicity. So this water and these carbon nanotubes, they kind of don't like each other so much, so they won't hug on the big surface. As the video will go, this actually also different speed of the impact. But even with higher speed, we can observe that it's not spreading on the surface. It just forms additional smaller parts and it breaks into smaller droplets. This is when we have tilted the sample. It will just bounce down a few times. So it's showing you that carbon nanotubes are very hard to wet, basically, by any liquid, water-based liquid. With ethanol, for example, let it be, it's much easier because the structure is a bit different. But for water, we can observe this bouncing. And this is, I think, the best part of this video that I like the most. It's like skateboard. You can use this water also a bit. And still, as you can see, it's not spreading on the surface. Can I use next slide? Okay. Okay, it will go, yes. So this is one of the, let's say, possible application of carbon nanotubes to use for some surfaces that we don't want to wet. In electronics, for example, in the PC, if we would throw water on that, we are safe because it won't absorb any water. This other, quite, I would say, popular application or aiming for this application is called space elevator. And the aim of this application is to have a space kind of elevator that goes up to the space station we have, for example. But we need to use basically the cable. The problem is the cable because we want to transport something from the Earth to the space. So first of all, the weight of the transported thing. Second of all, the weight of the cable itself. It cannot be also too thin because it will break. So for that reason, there are a bit of physics. I'm not sure if I want to actually explain that. I guess it's quite easy for you also. So basically the gravitation is going this way, the inertial force other way, and we want to balance it on the orbit around the Earth, on the same position kind of. So when the Earth is rotating, it rotates at the same position. And this is about comparison about the iron-carbon nanotubes. The tensile strength that you see is much higher for carbon nanotubes, with much lower density. With lower density, which is basically 5 times about, it means that the weight is smaller, and due to that, but also at the same time much stronger than steel or iron, so we could maybe potentially use it. And this is the cost, but it's not so important, I think. So how do we make it? This is called carbon nanotube yarns. Like the same way as we use the wool to make strings and then sew the clothes, the same way we can use carbon nanotubes to make the ropes or strings. Of course, the diameter depends on the strength of the carbon nanotubes we use, the height of them, and the number of such wires later on, and so on and so on. But using such a wire, we will decrease the properties of the individual carbon nanotubes a bit. However, in general, this will be much, much longer and stronger than the steel wires that we could possibly use. This is not a cheap operation, definitely. But if we talk about space and rockets and so on, nothing is cheap. So I guess it's probably okay to use this one in the future also. Actually, there's one big Japanese company which kind of said that they will build such a prototype up to 2021. So they have still 4 years, I guess. We will see. And yes, and this I was saying before, darker than black. What does it mean exactly? So this is just for the reminder. This is the optical range of light here. And as you can see, in order to obtain the black material, we need to absorb as much light as it's possible. Because in theory, all the colors originate from the reflection of the light and absorption and transmission of light in different manner, like this. So with electromagnetic radiation, we can absorb some light, we can transmit it or reflect. And the amount of the reflection and absorption and transmission tells us what kind of color we have. And based on that, we go to the other thing. So we have the black paint. Well, we don't have here, maybe this. So it's about absorbing about 75–85% of the light. Black tiles a bit more. There's some special black coating for the absorbing foil. It's 98. But already carbon nanotubes, it's 99.96%. And it's called so-called black body behavior, which is basically the theoretical material that absorbs all the light and don't emit anything. And I will show you in this video what does it mean. Maybe some of you already can notice. This is normal mask made of bronze. On this side, we can see only the contour. We don't see any details here. Is it flat or is it also 3D? Well, basically, it is 3D, as you can see all around. But it's so black that the reflection, diffraction, and other parts of the light are not reflecting like in this way. They're just absorbed. So we can observe basically black, flat screen, like without 3D kind of style. And this is made by some American company recently. They patented this method, which they claim is the darkest material ever. And we can use it for absorbers, for example, of course, which is quite obvious. But also, for example, if we want to have some thermal measuring device, we need to calibrate it on something. And they are also very useful for calibration of those. So as you can see, once again, there are no details visible, even though the thickness of this black layer is only 50 micrometers, 0.05 millimeter. It's very thin, but still you cannot see any detail. Everything is absorbed completely. And yes, let's go to this one. So I was talking about the conventional carbon-native forest, which is darker than black and so on. But there are also different types of carbon-native forests that we also use in the lab, like this frost column-like, because this is the frost column that you can observe in some parts of the world. And after applying this kind of carbon film on the top of such a carbon-native forest, we can get the chameleon, so-called layer. Everyone knows that chameleon can change the color depending on mood, basically. Not only, but also. And we kind of did the same thing here. In a way, this is the conventional carbon-native forest, which is always black. But as you can see, by changing the angle of the frost column forest, we can change the color from orange to yellow. We can do the same thing by applying a bit of a voltage here. And this is very good potential application for some displays also and so on. So maybe, I don't know, maybe in the future you will be using this part instead of LEDs or OLEDs and so on and so on. So I showed you from one side that it's very black, but now I'm kind of lying and it's colorful. And I will lie a bit more because the carbon nanotubes also can glow like this or this way. This is also from my lab. So basically, by applying additional modification of the structure of such a forest, carbon-native forest, we can basically make the emitters, green light emitters, of different intensity. As you can see, a bit slower intensity, a bit more bright. And this, for example, this sample was more or less constantly shining for 37,000 hours, which is, I think, 3 years about. So it's a lot, and it's quite stable emission for that part. So I'm lying kind of again, because I said it's only black, but it's also glowing in the dark. And this is a bit interesting, maybe also. Another possible application. Okay. I call it metamaterials. And this is a bit more complicated, but I will try to explain it very easily. Metamaterials are basically the materials that do not exist in nature. There are no such materials in nature. And this is basically some kind of structures that can interact with the electromagnetic radiation, for example, light. And they can bend light, basically. And by bending light, like here kind of style, as shown here or here, we can, for example, obtain invisibility cloak. Probably most of you have read or seen the movie Harry Potter, when he was hiding behind the cloak. And this is the style of material we can use for that. And carbon nanotubes also can be used for such structures in this kind of manner, with using very black carbon nanotubes in different structures like this. We can achieve similar effects already. And finally, maybe some quiz, let's say. I think it would be quite easy to guess what is this. This is made of carbon nanotubes also, because sometimes people are also bored in the labs. So they do many different things. So anyone idea what is this supposed to be? Exactly. Okay, let's go to the next one. You know this guy? Yes, it's Obama. Many of them. Some, I don't know, but I think it was American company. They decided to make micro Obama for some reason. The guy on the right hand, do you have idea when he's next to Obama? Who might it be? Hmm? Yeah, exactly, Joe Biden. So the vice president also. This is, I guess, very easy to guess what is that, because it's just clover. Let's call it bunnies, a bunch of bunnies. And I have no idea, something. Yeah, and I think here I will finish the talk. I tried to show you today that the science is not always very serious, and I'm lying all the time about being very black and very colorful and so on. But yeah, I said in the title of the topic that it's material of the future in a way, because there are so many possible applications for carbon nanotubes. Already people are using in cars, for example, new cars, already in the bumpers, and in some parts of the car, we use the composites to make them stronger. We already started to use the MEMS, so memories kind of, or electronics parts and transistors and so on. So it's getting, the price is still not the cheapest, but it's much better performance than silicon ones. So if we will, in general, as the researchers, we will work a bit more, we will have very good effects in the future. And thank you, that's all.